I'd like to talk about a new technology, relatively new, which is essentially following reactions in real time. But in order to talk about this, I need to provide a context. The context is single particle cryo-EM. And what is single particle cryo-EM? It's a method that was introduced some years ago for looking at molecules, but molecules didn't need to be in crystalline formation, but they can exist at single particles. And the idea is that in order to get all directional information for a molecule, we don't have to tilt it. The molecule already tilts itself. It exists in many, many copies in a solution, and all we have to do is take many different shots and then figure out how to put the data together. So this was sort of a single idea that I've been pursuing for a few decades, and that finally got fruition. And nowadays, it has, I believe, revolutionized structural biology. So nowadays, we have a structural determination workflow that goes all the way from protein purification, negative staining, specimen vitrification, data acquisition, and so forth, all the way to model building. And what is new most recently, a few weeks ago, is that atomic models can now be built using machine learning in the context of existing experimental data. So this is not like AlphaFold. AlphaFold rests on the knowledge that has been gained in decades of model building, but rather it is now a way of combining machine learning together with constraints provided by experimental data. So what has been achieved by single particle cryo-EM today? I only give a few examples that where my laboratory has made contributions, but in fact now thousands of structures are being solved experimentally by this method. So what is missing? Missing is really the dynamics. I'm showing you an example of dynamics that has been inferred not by some kind of following reactions, but rather by stopping reactions at known times by chemical means. And this is sort of, I would say, it's essentially cheating. We are not really providing dynamics, but we're stopping the reaction, and we don't know what kind of artifacts we introduce. And this is an example here from the early times when we wanted to know how the ribosome makes proteins. So we were able in 1998 to put together the entire workflow of the elongation cycle. But this is, as I said, cheating because it was done by using GTP analogs and antibiotics. And so right now I'm talking about starting and stopping reactions in real time using a microfluidic chip. And you can see the diagram there. The idea is we are mixing two components very fast within a millisecond or a half a millisecond, and then we have a reaction channel, and the reaction channel defines the time during which the reaction takes place. And at the end of the channel, we have a sprayer which is gas-assisted, and it sprays the reaction product onto the grid as the grid falls into the cryogen. We switched over from silicon chips to PDMS-based chips in order to be able to develop them faster and make them applicable in many different situations. And you see a diagram here. Changsong Feng is the person who contributed in great amount to this effort. So the latest example is a ribosome subunit association, which takes place essentially within a second or a fraction of a second. Ribosome subunit association is the basic function. It's part of the initiation, and during this time, the subunits find each other and associated to become a working ribosome. And we were able to follow this in real time, and we can exactly infer how the subunits come together and how the bridges form. And due to the lack of time, I cannot go into the details. So we can see how within 10 milliseconds the first association takes place, and then the exact configuration of the ribosome forms. Okay, thank you.
Thank you, Professor Frank.
I have a single slide which doesn't show. Never mind. My first disruptive technology contribution is to use the belt of my reserved pair of pants instead of slides. Our daily life relies on the function of a large number of different molecules: DNA, RNA, proteins, lipids, sugars, and so on. Structural biology unravels the mechanisms underlying these functions, as we have just heard in the preceding talk. Here, I want to illustrate this with one class of these macromolecules, namely proteins. And the theme that I want to address is in some way related to what we heard earlier today from Michael Jordan. When he talked about alpha-2, he mentioned the boundary problem. And what I want to talk about is how will we move boundaries? Will AI move boundaries, or will new experiments move boundaries? I'm convinced that it is new experiments which will then again provide information with which to train new algorithms, and so we will go step by step in this way. My belt serves to illustrate that proteins have a very simple chemical structure. They are linear arrays of building blocks. The start is defined and the end is defined exactly as in my belt. I can in no way understand the wide range of functions by proteins if I know only the chemical structure. I give you two examples. A common structure in proteins is the so-called antiparallel beta sheet, or a hair needle structure. In a hair needle structure, the strength of the polypeptide is comparable to steel. It's very hard. Another common structure that we find is the alpha helix. If we pull, there is no resistance. And that is what we find in our hair, for example. If we had the same in the ligaments in our knee, it would be a disaster. When we talk about drug development, if I only knew the chemical structure, I could target sequentially following residues in the structure. If I know the three-dimensional structure, then whenever there is a crossover in the three-dimensional structure, I of course get all of a sudden recognition points that are far apart in the chemical structure, and now all of a sudden form the receptor position where a drug can bind. So with this, I hope to have illustrated to those of you who are not in the field why it is important to know not only about the chemical structure of proteins, the same applies to DNA and RNA, but that we need to know the three-dimensional structure. How are these structures determined today? We have just heard a very nice example, cryo-EM, how proteins are isolated, purified, put on grids, and then frozen into liquid nitrogen. That's a very low temperature. If you use X-ray crystallography, you grow crystals and put them into liquid nitrogen at very low temperature so that everything gets rigid and can be observed in high precision. The technique that I use is nuclear magnetic resonance spectroscopy. There is a small step toward the real system in which we are interested. We can work in solutions that resemble body fluids, but this technique is limited to relatively small molecules. I'm talking about small proteins, not really small molecules, and we have, therefore, also the limit of low sensitivity. Now, when we work with the structures that have been determined for the isolated, purified proteins, we are limited. That is a very important boundary. I live this in our daily work in providing input as a basis for drug development. We use the structures, all kinds of structures that have been determined from isolated proteins, and we use these in combination with function assays of the same compounds that are performed in living cells or in higher organisms where we have a myriad of additional molecules in the solutions or attached to membranes that may influence the functioning of the proteins of which we have determined the structure outside of the living mechanism. Therefore, the outlook for the next decades is that structural biology will move toward being able of studying the behavior of the biological macromolecules in vivo, in living cells, and hopefully in higher living organisms. We are at the very start of this today. We have cryo-electron tomography, which provides us initial pictures, but at very low resolution. We also have NMR spectroscopy with living cells, which can give limited information today about the structure of proteins inside the cell, and more importantly, about interactions between molecules in the living cells. And we also have the possibility, which has been very little exploited today, to combine NMR spectroscopy that will provide us about information on structure and interactions with magnetic resonance imaging, MRI, that many of us have experienced in medical diagnosis. And there we can combine the information from spectroscopy with geographical information that we obtained from magnetic resonance imaging. This all is at the very early stage, and I see the future of the contributions from structural biology in development of methods that will improve these approaches, both by cryo-EM tomography and by magnetic resonance techniques combining imaging and spectroscopy. Thank you.
Thank you, Kurt. Thank you. 2021. David, over to you.
Thank you. All right, and I guess I've got an extra minute and a half, hopefully. So I'm going to try and convince you a little bit about the value of photons for chemistry and biology. So many years ago, myself and a few others had the idea of, would it be interesting to take the knowledge from inorganic chemistry, and specifically the idea of taking the knowledge of how to power the planet with solar energy, and take that chemical knowledge and translate it and export it into organic chemistry. We did that, and it led to this area, which is now known as photoredox catalysis. So photoredox catalysis, apart from the fact that it allows you to perform these really beautiful reactions and make some really nice videos along the way, it actually became a reasonably significant field over the last 20 years or so. So the initial papers in this area were published back in about 2008, and then last year, and between last year and this year, this will be well over 1,900 papers in this area. So the question is, why is it that taking that knowledge from inorganic chemistry and photons and moving it into chemistry, why did it become interesting to academics, but more importantly, why did it become interesting to the industrial world? Well, it became interesting in one way because it allowed the development of many new organic reactions, and many of those new organic reactions can power the development of new drug molecules and new types of drug molecules along the way. And these are just some of the companies who've actually been involved in doing this. I'll just show you one example. This is a relatively recent one, but from Novartis. This is a Rho kinase inhibitor, which is used in neuroscience. And the blue circle, which is on that molecule, is a bond that previously would not have been able to be made readily without the use of this new technology. And this is just to demonstrate that one of the kind of beautiful aspects of this is that you can now perform these chemical reactions on scale, actually using, this is blue light, this is visible light, being performed at Merck Process Chemistry in Rahway. But I didn't want to really talk to you mainly about chemistry. I really wanted to talk to you about how you can use photons and catalysis and use it to gain new insights into biology. But one of the key features here is the aspect that all the chemists around the world, in both academic and industrial settings, are now effectively have the infrastructure to perform photonic chemistry. So they can now use this to actually start to probe questions in biology at the same time. So what are the areas that this is being used for? So one area which has gained a lot of attention has been for biological interaction networks, or otherwise known as interactomes. And for those of you who don't know this, if you think about any biological molecule, for example, a protein of interest, most biologists can tell you that those molecules are constantly interacting in a dynamic fashion with lots of other molecules, whether it's other proteins, whether it's other metabolites, single molecules, signaling molecules, nucleic acid-based systems. And what's really interesting is the vast majority of these interactions are actually not known, and that becomes really important if you're thinking about disease state biology. So one of the questions becomes, how do you identify these interactions? So one of the ways that we started to think about this was, can you use proximity labeling? And the idea is, can you put a catalyst on your biological molecule of interest, for example, a photocatalyst, and then shine light on it, and now let that protein of interest go about its usual business. But now it will leave its footprints wherever it goes. It'll start to label everything it interacts with. So the applications of this become quite manifold, and this is just an example of being able to use this. These same photoreactors that were used for chemistry are now being heavily used now for doing this, for biology or for gaining insights into biology. So what are some examples of that? Well, this is one example. This is Herceptin. Herceptin is a well-known medicine for HER2-positive breast cancer. However, 70% of patients have primary resistance to this. But what you can do is you can put the photocatalyst on Herceptin and you can simply map the biological differences between the two different states. And you can start to determine the biological reasons why some people are susceptible, yet other people are resistant. And thereafter, we've now been able to develop a small molecule drug which allows you to now switch on Herceptin for cells that were previously resistant. Other things you can do, for example, is you can take the brain and you can actually start to think about ways to find small peptides that actually cross into the brain. And we've now been able to identify completely new receptors that allow small peptides to get into the hippocampus and do this selectively using receptors that were previously unknown. So the value of this is a bit like the metaphor of thinking about a small tugboat that can effectively drag an ocean liner into safe harbor, meaning that you can take these really small peptides now and they will effectively drag things like Taxol and even much larger molecules like antibodies into the brain based on a very small peptide sequence. But other aspects, just to sort of finish off with, has been in the neurodegeneration or the neurology area. One area in particular has been around studying TDP-43, which is heavily associated with ALS. And we've now been able to sort of figure out some of the key signatures that not only govern assembly of TDP-43, but also disassembly of it at the same time. So this, again, has gained a lot of attention. We actually recently entered into a pretty significant 10-year agreement with Johnson & Johnson, who have now, they're industrializing this technology, but all of these other companies are also working heavily on this, as well as Pfizer and Merck, which is obviously something that we're quite excited about. And I'll finish off by acknowledging, these are the folks at Princeton, many of them did this work, and lastly, thank you for your attention.
Thank you, David. Now we'll go back to Professor Zhang, if you're ready.
Thank you. Can you bring up my slides, please? In the 10 years since LIGO first detected a gravitational wave, we have improved our detectors so that several times each week, LIGO sees waves from colliding black holes. To achieve several per week, we use radically new squeezed vacuum technology, which is also called squeezed light. In this talk, I will describe in greatly simplified form how we conceived and perfected squeezed vacuum technology. It was a 50-year struggle, mostly in American universities with government funding, and in year 44, it began triggering spin-off into private industry. I'll conclude with comments on the danger that political turmoil in America may be destroying this university-based route for creating new technologies. In 1972 and 73, 3 foundations were laid for squeezed vacuum technology. The first foundation was when Rainer Weiss at MIT invented the gravity wave detectors that we ultimately would build for LIGO. In this simplified model, 2 mirrors hang from overhead supports at the ends of perpendicular arms. A laser beam shown in red monitors the difference in arm lengths by interferometry. A gravitational wave stretches and squeezes the arms oppositely, so the mirrors move in and out, and due to interference of the light, the output signal light brightens and dims. The second was that upon learning of Weiss's invention, Vladimir Brzezinski in Moscow warned us that the gravitational waves might be hidden by the mirror's quantum fluctuations a tiny shaking, a billion times smaller than an atom that can never be stopped. To conquer this mirror shaking, Brzezinski said that we must create some sort of quantum technology. Third, the key to that technology, vacuum fluctuations, was laid by another Russian, Yakov Zeldovich. Imagine a box filled with nothing, only a vacuum remains. The vacuum is filled with tiny fluctuations of everything that ever could reside inside the box, vacuum fluctuations. Zeldovich speculated, and he was probably right, that the Big Bang explosion that created our universe produced only vacuum fluctuations and nothing more. But those fluctuations, by feeding off the energy of the universe's expanding space, transformed themselves into all the matter that fills our universe today. Now, these three foundations were followed by a decade of frustrating gestation. From 1973 to 1981, Brzezinski and I and our students struggled to invent a quantum technology that protects the gravity wave signal from the mirror's quantum shaking. We found nothing very promising until one day in 1981, my student Carlton Caves had a brilliant insight. Vacuum fluctuations of light entering the interferometer backwards can control the mirror's shaking, Caves realized. In technical language, the vacuum fluctuations, by beating against the laser light, create fluctuating light pressure that controls the mirror's quantum state. Perhaps, Cave speculated, just as the Big Bang manipulates vacuum fluctuations to create all our universe's matter, similarly, we humans can manipulate vacuum fluctuations so that they do what we want, prevent the mirror's quantum shaking from hiding gravitational waves. And Cave figured out the precise manipulations to do that. Squeeze the vacuum fluctuations, reduce one aspect of them while increasing another in precisely the right way, a different way at different frequencies. In 1983, Jeff Kimball invented a powerful technology for squeezing the vacuum. In technical language, send the vacuum fluctuations through a carefully tuned laser-pumped nonlinear crystal, and then through a long filter cavity. Next came a 36-year struggle to build and perfect Kimball's squeezer, make it strong, accurate, and robust. Kimball at Caltech worked the problem for a decade, and then LIGO research groups took over at MIT and in Germany and Australia. And finally, in 2019, a simple form of squeezing was mature enough to be implemented into LIGO. Almost miraculously, this brought a 50% increase in detections of colliding black holes, signals that had been hidden by the mirror's exceedingly small quantum shaking. Seeing LIGO's success, private companies then embarked in 2019 on implementing squeezed vacuum technology into their own technologies. Xanadu for photonic quantum computing, and with DARPA impetus, miniaturized squeezers to use in gyroscopes and magnetometers for navigation. In the meantime, in 2023, LIGO implemented a more powerful variant of squeezing, bringing us to several black hole collisions each week. This history of squeezed vacuum technology is similar to that of some other radical new technologies. Foundations and then gestation in American universities, often with international stimuli. The technology, with risk of failure, is brought toward maturity for 10 or 20 years or more in universities with government funding, and then private companies then and only then see the possibility of profit at acceptable risk and begin investing heavily. The Trump administration's attacks on American universities are endangering this route for new technologies. Alternative routes are needed, preferably routes with strong international collaboration, so that no nation can gain an advantage by single-handedly bringing a powerful, disruptive new technology to maturity. Thank you.
Thank you, Kip. And I think you were concluding there some of the points I was making about the potential crisis in science and the lack of trust in science that we're starting to see at government levels. We're now going to go back to Professor Zhang. I think you have your slides. Ready to go?
Okay. Ladies and gentlemen, it's my honor to talk a little bit single atom catalyst, a new frontier materials in the chemistry. So, overview of the single atom catalyst, catalysis play a very important role in our society, particularly with catalyst, we can produce a fertilizer with food, and we produce polymers, so we can have enough clothes. So catalysis is very important. And before my work, for the commercialization catalyst, normally with nanoparticles, cluster, and sometimes also with single atom. But it's mixture, so people don't know which one is the actual size, nanoparticles or single atom. So about 20 years ago, I discussed with my students, try to design a new kind of catalyst, which is all the single atom was on the support, was isolated on the support. So with such kind of catalyst, can we find some new chemistry? So after a few years, we are very successful. So we published the first paper, the single atom catalysis. We coined the new concept in 2011. We gave a clear definition about the single atom catalyst, which means the core metal atoms was separate each other and only interaction with support. Now, this kind of new concept is very popular and receive much attention from the society. The paper ranking the #1 most cited research paper in Nature Chemistry up to now. And then after our work, you can find a lot of paper published. Although we began from the noble metal, now almost all the important metal in the periodic table was reported to be a single atom catalyst. And you can find up to now more than 50 reactions was reported to use the single atom can obtain very good performance, not only activity, but also just selectivity. So you can find from 2011, after our work, there are 20,000 papers was published in this field and more than 1 million citations in this field. So single atom catalyst has become a most active topic in the catalysis. Actually, not only catalysis, but also in the whole chemistry and materials and also other fields use the single atom catalyst concept. And in the world, more than 100 countries and more than 1,000 research groups follow our new concept, the single atom catalyst. And the Chemical and Engineering News highlight our work, top 10 achievement in chemistry in 2016. And last year, I'm very happy to receive the citation laureates and for the seminal contribution to the single atom catalysis up to now. 89 citation laureates go on to Nobel Prize. So you can find for the conventional, traditional catalysis, we have many important concepts. And during the last 33 decades, you can find many important concepts for the nano catalysis. Now, with our single atom catalyst, you can find people can understand catalysis from micrometer to nanometer, and now we can to atomic scale level. So the single atom catalysis is very important. It's one of the reasons to receive so much attention. So now we try to use artificial intelligence. Before, because the nanocatalysis is a mixture, it's a nanoparticles, cluster, single atom, so it's quite difficult to obtain reliable data. Now with single atom, it's possible. And also with a single atom, we can obtain clear structure activity data and the spectrum structure data. And we learned from the Nobel Prize in Chemistry 2022, learned from the protein prediction. So now we can predict our original design of our catalyst. This is some advantage and disadvantages. I don't have time to give more details. So now in our laboratory, we try to set up such kind of big data to try to establish the structure, spectrum, and the reaction database for single atom catalyst. So some opportunity and challenges. Now the synthesis is very important, particularly atomic manipulations challenges, and characterization is also very important. And also we need time to understand the physical and the chemical origins, and also the theoretical understanding of the original design of a single atom catalyst is very important. For the commercialization, there are many process has report to use a single atom catalyst, and particularly for the energy conversion reaction, you can find the water splitting, carbon dioxide conversion, and nitrogen activation use our single atom catalyst. So single atom catalyst play a very important role for the carbon neutrality in the future. So summary, the single atom is a very hot frontier concept in catalysis, but also in the chemistry and the materials. Single atom catalysts provide atomic scale understanding in heterogeneous catalysis, regional design, try to combine single atom and artificial intelligence is very possible. And commercialization important. Green hydrogen production, carbon dioxide conversion is very promising. And particularly because the single atom, we have used autumn every autumn. So autumn efficiency is very high. So catalyst will be low. So low cost single atom will play very important role in the carbon neutrality. Thank you very much for your attention. Thank you.